let's look at some of the properties of the z-score distribution. This is a picture of the z-score distribution, and you should recognize the shape by now. This is called what? A normal distribution. All right, the scores are normally distributed. That means that it has this basic shape. All right, and for the z-score distribution, we would say this is mesokurtic. Do you remember that? The distributions that are normally distributed can be mesokurtic, leptokurtic, which would mean that it goes up here. Remember, you have to leap over a leptokurtic distribution, right? And then there's platykurtic, the platypus. And a platykurtic distribution is flatter than the mesokurtic. Meso is in the middle. And so the z-score distribution is considered to be mesokurtic. Okay? All right. So let's look at some additional properties here. First of all, is hypothetical. It's a plot of all possible z-scores in the universe and beyond, past, present, and future. So obviously that's got to make it hypothetical, right? So it's a plot of every single z-score you could ever have. So that makes it hypothetical. And that's why we see this nice smooth line here. If you're plotting all possible z-scores in the universe and beyond, that means that there's going to be a lot of, there's going to be people getting this z-score, and then, instead of -3, this could be minus 2.99999, and then minus 2.9998, etc. So when you have every possible score being represented, you get this nice, smooth, flowing line. Remember that? All right. Now, the mean of this distribution is 0. And notice how I've used the parameter. Can you recall, why are we using the parameter here? Remember, parameters represent populations. Parameters are statistics calculated on populations. And if we've got a plot of all possible z-scores, that's a population. And so we're going to use parameters. So the mean of this distribution is 0. And most z-scores, this might surprise you, but by far the vast majority of z-scores in the universe and beyond are somewhere between -3 and +3. All right, so if somebody says, I got a z-score of 692, wow, 692, that would be way off the charts, right? Because again, if you look at all z-scores in the universe and beyond, the vast majority are between -3 and 3. The variance, remember the symbol for variance? The variance of this distribution is 1, which means the standard deviation is 1. Because if you were to take the square root of the variance, what's the square root of 1? It's 1, right? So the variance is 1 and standard deviation is 1. Now, these do not change. When I say mu is 0, variance is 1, standard deviation is 1, that is always going to be true. All right, and actually you're going to do an SPSS assignment, and you're going to see that for yourself. All right, I don't want to give it away, so I'll let you be surprised and amazed. Well, maybe not amazed, but anyways. All right, what about the tails? Hypothetical. So hypothetically, this negative tail extends to infinity, and this positive tail extends to infinity. All right, so in theory, we could get a z-score of any size. That makes sense. If you think that it goes from negative infinity to positive infinity, that means any z-score is possible. The area under the curve is 1 or 100%. So I hope you remember that when we talk about area under the curve, we're talking also about probability. So I could rewrite this and say the probability of being somewhere in this distribution is 100%, or in decimal format, I would say 1. Okay. So if this is a hypothetical plot of all the IQs in the world, in the universe, past, present, and future, if this represents IQ, and then I said, what is the probability that you are somewhere, your IQ is somewhere in under this curve? It's 100%. I guarantee you, if I've plotted all of them, you're somewhere here. So the total area under the curve is the total probability, and that has to add up to 1 or 100% if you're using percentages. You might remember this from when we learned about averages, mean, median, and mode. If the distribution is perfect, in other words, perfectly normal, and if it's hypothetical, it would have to be perfect, right? Hypothetically, that means it's symmetrical, which means that the mean, the median, and the mode are all found right here at 0, right? And this makes sense. The mode is the most frequent score, and of course, this red line here represents frequency. So this is the most frequent score. Whatever is under this peak is the most frequent score, and that happens to be 0. So 0 is the mode. Now, it's also the mean, right? Because remember, the mean is the fulcrum, the center of gravity. So if this were a teeter-totter or, seesaw, the fulcrum, the point at which it balances, would be right here in the middle. The weighted distance of all the scores below 0 would equal the weighted distance of all the scores above 0. Remember we talked about frogs, right? The 80-pound frog over here would balance out the 80-pound frog over there. All right, so this distribution is perfectly balanced. This is the center of gravity. This is the mean of the distribution. And it's the median because, remember, it's symmetrical. So 0 would cut the distribution in half, such that this half here, this left half, is a mirror image of that half. So it cuts all these scores exactly in half. All right, mean equals median equals mode when we're talking about the z-score distribution. Now you might notice that I'm using or I'm emphasizing the word the z-score distribution. Or is it the? Well, the z-score distribution. And I'm emphasizing that because we can certainly take, 10 raw scores and convert them to Z. That doesn't mean we have all Z scores in the universe and beyond, does it? We only have 10. So when we have 10 Z scores, you're not going to get something that looks like this. All right? This is what you see when you plot all possible Z scores, when you have the Z score distribution. Okay, the distribution is also asymptotic or asymptotic. All right, and what does that mean? It means that this line here that represents frequency, it gets closer and closer and closer and closer to the x-axis, but it never actually touches. And that's true in this direction as well. Now, I will point out something that is important, and a lot of people get confused initially. I'll say something like, which z-score is bigger? Is bigger. Which z-score is bigger? -2 or +1. Now, from your math classes, you would say, well, +1 is a bigger number than -2, and that's because you're focused on the negative. That does not hold true for a standardized distribution like Z or T. When we're asking about which z-score is bigger or which t-score is bigger, the only thing you look at is the number. Do not look at the sign. So if we ignore the sign, then this z-score, right, 2, because we're ignoring the sign, is bigger than 1. All right? The negative just means below average. It doesn't mean smaller. It means below average. And the positive numbers are above average. And I've mentioned this, but doesn't hurt to repeat. This red line here represents frequency. So you can now see that because these are the most frequent numbers, right down here, these are the most frequent, they have the highest frequency. These z-scores occur more often than z-scores that are out here in the tails, right? These have lower frequencies, which are lower probabilities. So now we have a very good definition of what is an outlier. Remember when we talked about outliers before, we just kind of defined them as the black sheep, right? And they were the black sheep because they stood out. So an outlier was a number that was either really, really big, and in that and if it's really, really big in comparison to almost all the other scores, which are really small, then that big number is going to stand out, and you would have said, oh, it's an outlier, it stands out. Same thing in the opposite direction. You could have a number that's really, 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 really small, and all the other numbers are really big. Then that really small number is going to stand out as an outlier, as a black sheep, right? It stands out in the crowd. Well, that definition worked up until this point in time. Now, moving forward, if I ever ask you for the definition of an outlier, you need to use this statistical definition, which basically says that an outlier is any raw score that when you convert it to Z, it is going to be beyond, that means larger than 2.58 in either direction, or beyond 3 in either direction. So let's use that first one, 2.58. So let's just say 2.58 is around here, right? So if you were to get a z-score in this part of the tail, so it would be larger than 2.58 in this direction, that would be an outlier. Same thing, if we use 2.58 here, this is negative 2.58. Anything beyond, so in this tail here, anything beyond 2.58 is an outlier in that direction. Now, some people like to use this definition of an outlier, but some people like to just use 3. It's a nice kind of, neat, easy number to remember, and they'll say anything beyond plus or minus 3. So that means now you have to be either here or here, all right? So if you were negative 2.75, would you be an outlier? Not according to this definition, right? You have to be larger than negative 3 if you're in this tail. So negative 2.75 would not make you an outlier, but it would if you're using plus or minus 2.58, right? Because you would be bigger than 2.58 if you were here, all right? 2.75 would be, it would be large enough to have you be identified as an outlier. Okay, let's see, what else? Numbers on the x-axis are called a standard deviation unit. So what that means is if we look at this 1, right, we want a unit of measurement. Is this 1 mile? Is it 1 inch? Is it 1 centimeter? No, it's none of those. It is 1 standard deviation unit. So if you were to get a z-score of 1, that would mean you are 1 standard deviation unit above 0. If you were to get a z-score of 2, that would mean you're 2 standard deviation units above 0. So this is a unit, this is a unit, this is a unit. Same thing in the opposite direction. Here's a unit. Here, if you had a z-score of -1, you would be 1 standard deviation unit below 0. Here you are 2 standard deviation units below 0. Okay? All right. Oh, you know what? I want to go back for a second because there is one thing that I have noticed students get really, really confused about. And honestly, I think it's because they don't draw out this distribution. And so it's easy to maybe get confused. But let me just point something out, and I hope that moving forward, if I ask you a question about this, you will all become really proficient drawers of a normal distribution, and you'll draw it out so you don't make this mistake, okay? So let me explain what I'm talking about. I often ask the question, I'll say like fill in the blank. As Z increases, okay, moves away from 0 in either direction, frequency decreases and probability blank. Okay, so you have to fill in the blank. And it's an easy question when you've drawn this out so you can visualize it. But without visualizing it, you can very easily make a mistake. Okay, so let's look at that. We said as Z increases in either direction. So here Z is going up, right? You start at 0, Z equals 0, and then you're going up, Z is 0.5, 1, 1.5, 2, so Z is increasing. But it's also increasing in the negative direction, right? Remember we talked about that a few minutes ago? So here, negative 0.5, negative 1, negative 1.5, this means Z is increasing. So as Z increases, so we're moving along the x-axis, what happens to frequency? Frequency is beginning to drop, right? So Z is going up, frequency is dropping. That means probability is also dropping. As frequency drops, probability drops. Okay? So the area under the curve, and you can see that. The area under the curve, if you're at 0, is large, and as you increase our Z scores, as you move along the towards the positive end or negative end, you move away from 0, what's happening to the area under the curve? It's beginning to shrink, right? The area under the curve here is far less than what it was in the middle. So again, as scores increase in either direction, as you move away from 0 on the x-axis, frequency of those scores drops, and so does probability. It begins to shrink. Okay? Easy concept when you're looking at the distribution. When you're not looking at the distribution, trust me, a lot of good students, a lot of great students have made that mistake on an exam.